Assalamu alaikum everyone. This is the second lecture of parallel resonant circuits of the course EE-212. In the last lecture we started with the basic characteristic of the parallel resonant circuits. So I will summarize it by using the admittance curve that we have drawn in the last lecture, and we defined three regions. One was at omega naught, one was before omega naught, omega less than omega naught, and the third was at omega greater than omega naught, and it was a admittance curve. So what we found in the analysis is that at omega naught the admittance was purely conductance. So conductance is actually the inverse of resistance, and we found out that at the resonant frequency the admittance of the circuit becomes conductance. For omega less than omega naught, the circuit becomes inductive, or you can say that admittance is actually dominated by the inductive susceptance. IL is actually greater than IC for omega less than omega naught, because XL is smaller than XC and BL is greater than BC. The B is the susceptance, X is the reactance, and I is the current. So this is reactance, susceptance, and current. Similarly, for omega greater than omega naught, the circuit becomes capacitive or dominated by capacitive susceptance, and by this statement we mean that IC is actually greater than IL. So the current through the capacitor is greater than current through the inductor, because XL is greater than XC and BL is smaller than BC. And at omega is equal to omega naught, the circuit is purely resistive. IC is actually equal to IL, they cancel out, and the source current is equal to IG, the current that is passing through the conductance. At the end of the lecture we calculated the formulas for the quality factor. They were R omega naught C over G, where G was inverse of resistance, and R over omega naught L. And these were the formulas that we calculated for the quality factor. Now moving on towards today's topic, transfer characteristics of the parallel resonant circuit. So if I have to draw the circuit, it's actually resistance, inductance, and capacitance. This is the input current, IR the current through resistor, IL the inductance current, and IC that is the capacitive current, and the voltage is Vs. And if I have to calculate the output voltage at this point, Vout, that is actually equal to Vs. So Vout is equal to Vs, because all the elements are in parallel, so the whatever the voltage is at the input, it is appearing across all the elements, so the V output is actually equal to the source voltage. Now if I have to find V output over I in, so this is the output quantity, voltage in the output, and this is the input quantity, input terminal quantity, that is I in, the current at the input. This is actually the transfer characteristic that we have to analyze. Now if I have to find the output voltage, that is actually equal to the input current divided by the total admittance. So this is your admittance. And we know that the admittance is actually equal to the summation of conductance, capacitive susceptance and inductive susceptance. And after simplifying it, it will become J omega C minus 1 over omega L. So that's your total admittance. Now the V output equation will become I in over G plus J omega C 1 over omega L. And if I'll take this input current to the other side of the equality, V out over I in, it will become 1 over R plus J omega C 1 over omega L. And this is conductance, which is actually the invert of resistance. Now calculating the magnitude of the transfer characteristic, I in is actually equal to 1 over 1 by R square plus omega C minus 1 over omega L square root. So this is your transfer function. Now we have to find the cutoff frequencies. So if I have to find the maximum value of the transfer characteristic, that will be equal to R, because we will have the maximum response at omega naught. By the definition of resonance, we know that when the system is in resonance, the maximum response will occur, and it always occur at the frequency known as the resonant frequency, and that resonant frequency will make the impedance equal to resistance or admittance equal to conductance. So if I have to find the maximum value of V out over V I in, it will be resistance, and it will be occurring at the value omega naught, which is the resonant frequency. So now for the half power frequencies, the term V out over I in maximum was equal to resistance. For the half power frequency, it will become R over under root 2. R over under root 2, that is actually equal to V out over I in magnitude, and from here we know that V naught over I in is actually 1 over under root 1 over R square plus omega C minus 1 over omega L square. So after inverting, under root 2 over R equal to 1 over R square plus omega C 1 over omega L square. So this is the value. Squaring, it will become 2 over R is equal to 1 over R square plus omega C minus 1 over omega L square, and after simplifying it, it will be 1 over R square is equal to omega C minus 1 over omega L square, and after taking the square root, it will be 1 over R is equal to omega c minus 1 over omega L. So this will be your equation A. So I will write down the equation A again. So it was plus minus 1 over R is equal to omega c minus 1 over omega L. Now we have to find the upper and lower cutoff frequencies. For lower cutoff frequency, omega should be less than omega naught, right? So if omega is less than omega naught, so this term omega c minus 1 over omega L, so this term, that is inductive susceptance, it will be a bigger value than omega c, which is capacitive susceptance. So it is dominated by the negative portion. So this term of equation A will become 1 over R minus omega c minus 1 over omega L. And for the region omega less than omega naught, we already know that it is the inductive region, so IL will be greater than IC, and the XL, which is the inductive reactance, that will be smaller than XC, and the inductive susceptance will be greater than capacitive susceptance. Similarly, for omega greater than omega naught, we have omega c minus 1 over omega L. So if this omega value is a larger one, so the whole term will be a smaller value, and if omega is a larger value, this term will be a larger value. So omega c is actually dominating. So for omega greater than omega naught, the region is capacitive. We have IL less than IC, XL greater than XC, and actually it's less than IC, and inductive susceptance is less than capacitive susceptance. So the equation A for the second region, omega greater than omega naught, will become 1 over R is equal to omega c minus 1 over omega L. So from equation number 1, you will calculate the lower cutoff frequency. And from equation number 2, you will calculate the upper cutoff frequency. Now solving equation number 1, it was omega c minus 1 over omega L is equal to minus 1 over R. Omega square LC minus 1 is equal to minus omega L over R. And by further solving, it will become omega square LC plus omega L over R minus 1 is equal to 0. Now if I will take the term LC common from the whole equation, it will become omega square plus omega 1 over RC minus 1 over LC. So this is a quadratic equation, so we can solve it by quadratic formula. We know that A is equal to 1, B is equal to 1 over RC, and C is equal to minus 1 over LC. And after solving by using the formula, omega low is equal to minus B plus minus under root B square minus 4AC over 2A. I get the formula for the lower cutoff frequency, that is equal to minus 1 over 2 RC plus minus under root 1 over 2 RC square plus 1 over LC. So now we have the positive values as well as negative values, but frequency value is always positive, so I am only considering the positive values for the frequency. So the final formula for the lower cutoff frequency will be omega L is equal to minus 1 over 2 RC plus 1 over 2 RC square plus 1 over LC. Similarly, by using equation 2, you can calculate the upper cutoff frequency, that will be equal to 1 over 2 RC plus 1 over 2 RC square plus 1 over LC. Now if you have to find the bandwidth, so bandwidth is actually the subtraction of lower cutoff frequency from the higher cutoff frequency. So I will state it here, it will be WH minus W low, and it will become minus 1 over 2 RC plus 1 over 2 RC square plus 1 over LC. It is plus and minus 2 RC plus 1 over 2 RC square plus 1 over LC. So this is the negative. So these two values will cancel out, and we have 1 over 2 RC plus 1 over 2 RC. And the bandwidth formula will be 1 over RC. Now for the multiplication of upper and lower cutoff frequencies, multiplication omega low into omega high will be equal to the values 1 over 2 RC plus 1 over 2 RC square plus 1 over LC into minus 1 over 2 RC plus 1 over 2 RC square plus 1 over LC. So I can use the formula A plus B into A minus B is equal to A square minus B square. So WL into WH, lower cutoff frequency and higher cutoff frequency multiplication, is actually equal to 1 over 2 RC square plus 1 over LC under root square minus 1 over 2 RC square. So that will become 1 over 2 RC square minus 1 over 2 RC square plus 1 over LC. So these two terms will cancel out, and the multiplication of lower and upper cutoff frequencies is actually equal to 1 over LC, which is equal to omega naught square, and from here omega is equal to under root omega low and omega high. So the resonant frequency, again like in the resonant series circuit case, is actually the geometric mean of upper and lower cutoff frequency. So resonant frequency is the geometric mean of cutoff frequencies. Now we know that bandwidth is actually equal to omega naught over quality factor, and if I have to find the quality factor, that will be omega naught over bandwidth is equal to RC over under root LC, R under root C over L. So this is the third formula for the quality factor, which is only in terms of the circuit elements. So now if I have to find the formulas for the lower and upper cutoff frequencies in terms of quality factor and resonance frequency, I will use these formulas, and by substituting the final formulas for the upper and lower cutoff frequency will be omega naught minus 1 over 2q plus under root 1 over 2q square plus 1. And for the upper cutoff frequency, it will be omega naught 1 over 2q plus 1 over 2q square plus 1. So these are the formulas for the lower and upper cutoff frequencies in terms of quality factor and resonance frequency. An example, we are given a circuit in which the resistance is actually equal to 1 kilo ohm, inductance is equal to 10 millihenry, capacitance is equal to 100 microfarad. Now what we have to calculate: lower and upper cutoff frequencies, resonant frequency, quality factor, and bandwidth. So we will start from the resonant frequency. Omega naught is actually equal to 1 over under root LC. We know the value of inductance, also the capacitance, so it will be 1 over 10 millihenry into 100 microfarad. So the value for the resonant frequency will be 10 raised to 3 radian per second. Now to calculate the quality factor, it is R under root C over L and also omega naught over bandwidth. We know the values of resistance, capacitance and inductor. By using these values, we calculated the quality factor to be equal to 100. And from the second formula, Q is equal to omega naught over bandwidth, we can calculate the bandwidth is actually equal to omega naught over Q, and omega naught is 10 raised to 3 over 100. Bandwidth is equal to 10 radian per second. So now for the upper and lower cutoff frequencies, we can either use one of the formulas that we have derived. The first one is in terms of the quality factor and omega naught, the resonant frequency, and the second one is in terms of the circuit elements. So you can use either of these formulas to calculate the upper and lower cutoff frequencies. But the other way that we can use is, we know the resonant frequency, it is actually 1000, and then there is one upper cutoff frequency and one lower cutoff frequency. We know the bandwidth, it's actually equal to 10 radian per second. So if I will divide this bandwidth into two equal parts, it will be 5 radian per sec, and then again it is 5 radian per sec. So if I have to calculate the lower cutoff frequency, omega low, that will be equal to 1000 minus 5 radian per sec, it will be 995 radian per second. Similarly, for the upper cutoff frequency, we have 1000 plus 5 radian per second, and it will be 1005 radian per second. So this was the first example. Now we have another example in which we are given with a parallel resonant circuit. And the characteristics are omega naught is equal to 12,000 radian per second, admittance is equal to 5 millisiemens at omega naught, inductance is equal to 0.1 millihenry. We have to find R and C, resistance and capacitance values. Now first we can calculate the capacitance value. From the resonant frequency formula, omega naught is equal to 1 over under root LC. We know the resonant frequency value and inductance value. From here we can calculate the capacitance, that is equal to omega naught square L. the value will be 69.4 microfarad. Now for the value of resistance, we know that at resonance the admittance is actually equal to conductance, and this conductance is 1 over R. So admittance is actually equal to 1 over R. If I have to calculate the resistance value, it will be 1 over Y, 1 over 5 into 10 raised to minus 3, and the resistance value will come out to be 200 ohm. The next topic that we are going to discuss today is the real parallel resonance circuit. By real, we mean that we are going to consider the resistance of the inductor as well. So if I will draw the circuit, it will become capacitor, then there is resistance of the inductor, and then the inductor value. So there is a voltage that is applied at the input terminals, then there is current I. It is splitting into two different parts. One is passing through the capacitor and the other one is passing through the resistor and inductor branch. So this is a realistic parallel resonance circuit, and it is also known as tank circuit. Whenever we have a wire, we cannot assume the resistance of that wire to be equal to 0, because there is always a finite resistance present in a conductor. So to assume the real parallel resonance circuit, we have to introduce the resistance effect in series with the inductor. So now if I have to find the admittance value, that will be Y is equal to j omega c plus 1 over R plus j omega L. So that was the inductive susceptance. So we have added the resistance value with the inductive reactance value. So when I will take the inverse, that will become the admittance. So after solving, it will become j omega c plus 1 over R plus j omega L into R minus j omega L over R minus j omega L. J omega c plus R minus j omega L over R square plus omega square L square. So after simplifying, it will become R square omega c plus omega cube L square c j plus R minus j omega L over R square plus omega square L square, R over R square plus omega square L square plus R square plus omega square L square minus omega L over R square plus omega square L square. So these two terms will cancel out, and the final admittance term will become R over R square plus omega square L square plus omega c minus omega L over R square plus omega square L square. So this is your imaginary part and this is your real part. Now we know that at resonance, the imaginary part of the admittance is actually equal to 0. So after making the imaginary part equal to 0, what is the imaginary part? This one. So at resonance, the imaginary part of admittance is 0. So I will make omega c minus omega L over R square plus omega square L square equal to 0. And after simplifying, equal to 0, and Taking omega common from all the terms, it will become omega r square c plus omega square l square c minus l equal to 0. And it will become r square c plus omega square l square c minus l equal to 0, and from here we can calculate omega square is equal to l minus r square c over l square c, and by further simplifying it will become omega square is equal to 1 over lc minus r square over l square. Omega is actually equal to 1 over lc minus r square over l square. For the realistic parallel resonant circuit, we have an extra term r square over l square that is added to the resonant frequency term, that was omega naught is equal to 1 over under root lc, and this was for the ideal circuit. By ideal circuit we mean R is equal to 0 for the inductor branch. For the realistic parallel resonance circuit, if you increase the resistance value, you are going further away from the ideal circuit. If you have to make the resonance frequency of the real parallel resonance circuit equal to the omega naught, which is the resonant frequency of the ideal circuit, or approximately equal to omega r, approximately equal to omega naught, what you have to do, you have to decrease the value of resistance. So smaller the value of resistance, the real circuit will act as close as possible to the ideal parallel resonant circuit. So to make omega r equal to omega naught, r should be equal to 0. So this was the resonant frequency formula for the realistic parallel resonance circuit. And this was the last topic of this lecture. So in this lecture, what we have studied, we started from the brief introduction of what we have done in the last lecture. We started from the transfer characteristic. We derived the formula for the transfer characteristic. So we calculated two different regions, for one for the omega less than omega naught, from where we calculated the low cutoff frequency. The other one is omega greater than omega naught, there we get the higher cutoff frequency, and after solving the equations we got the formula of upper and lower cutoff frequencies in terms of circuit elements, as well as in terms of quality factor and resonant frequency. And in the second part of the lecture we started with a resistance introduction with the inductor, which make the parallel resonance circuit a real one, because the resistance of the inductor is never 0, it has a wire, and we have to introduce a resistance in series with the inductance value of the inductor. And after solving the formula of admittance for this particular tank circuit, we got the value of omega r, which is the resonant frequency of the real parallel resonance circuit, and it has an extra term which is dependent on the value of resistance. So if you have to make the circuit ideal, you have to decrease the value of resistance, and the omega r will be equal to omega naught when the resistance will be equal to 0. So this was the second lecture on parallel resonance circuit. So if you have any question, you can ask me through email. And that's all for today. Thank you.